All right, so today, like I said, we're going to start a little mini unit. All right, it's just going to cover complex numbers. Um, and then tomorrow we'll start working on trigonometric form of complex numbers. All right, so today we're just going to talk about I, which you should remember from Algebra 2. We're going to add, subtract, and multiply complex numbers. We'll use complex conjugates to divide complex numbers. And of course, find some complex solutions of quadratic equations. All right, so do be mindful, all right, that the imaginary unit I is equal to the square root of -1. All right, therefore I squared is equal to -1. And actually, you can kind of keep going with this. All right, so I cubed, which is equal to I squared times I, right? So that's equal to -1 times I, which is simply -I. All right, I to the fourth is equal to I squared times I squared, which is equal to -1 times -1, which is equal to +1. All right, and then from here, things just kind of repeat themselves. All right, so I to the fifth is going to equal I to the fourth times I. Of course, I to the fourth is just 1, and 1 times I is just I. So now we're back to I. All right, just for the sake of continuing. All right, I to the sixth is going to equal I to the fifth times I. Well, we know I to the fifth is just the same as I. So this is I times I, which is I squared, all right, which again is -1, right? So this pattern's just going to repeat, all right, which means I to the seventh is going to be the same as I to the third. I to the eighth is going to be the same as I to the fourth. And then you repeat that process all over again. I to the ninth would just be I. Okay? So it's actually quite easy to do I to any power, right? So you could do I to the 63rd power, for instance. All right? Well, all you have to do is divide this by 4 and find the remainder. All right? So 63 divided by 4 is equal to 15 with a remainder of 3, which means that I to the 63rd power is the same as I cubed, because that's what the remainder, 3, is. So this is -I. So what would I to the 104th power be, for example? Well, yes. All right. So this would be the same as, now the remainder here is 0, right? But 0 is kind of the same as 4, right? We go 1, 2, 3, 4, which is the same as 0, right? So this is going to be the same as I to the fourth. So this is just going to equal 1, right? So I to the, oh, I don't know, maybe 250th. All right, well, if you divide this by 4, all right, you're going to get a remainder of 2. So this is the same as I squared, which is -1. All right, so that's kind of how you can think of high powers of I. Okay, By adding real numbers to real multiples of I, you obtain the set of what we call complex numbers. All right. Each complex number can be written in the standard form a plus bi. All right, that's very important. All right, for example, the standard form of the complex number, the square root of -9 minus 5, is -5 plus 3i. In the standard form a plus bi, the real number a is called the real part of the complex number, and the number bi is called the imaginary part of the complex number. Right? And we should have seen all of this so far in Algebra 2. So hopefully none of this is new yet. Okay, so equality of complex numbers. Two complex numbers, a plus bi and c plus di, written in standard form, are equal to each other if and only if the real parts are equal to each other, so a and c, and the imaginary parts are equal to each other, so in this case, b and d. It's pretty, intuitive, right? In order for things to be equal, their parts have to be equal. Okay. All right, so a very easy example here. All right, if we have a minus 3i is equal to 2 plus di, all right, what does a have to equal here? Right, which is 2, right? And what does d have to equal here? Almost -3, right? Because this minus here. Okay. So, that's really all there is to it, right? It's pretty intuitive, pretty easy. Each part has to be equal. Okay. So when you're adding and subtracting complex numbers, right? So if a plus bi and c plus di are two complex numbers written in standard form, then their sum and difference are defined as follows, right? So the sum, to add, right? All we do is add the real parts, a and c, and all we do is add the imaginary parts, b and d. For subtraction, we simply subtract the real parts and subtract the imaginary parts. Okay, so just some examples here. All right, so first, if we have 3 minus I plus 2 plus 3i, so we're adding. So we add the real parts. So 3 plus 2 is 5. All right. And we add the imaginary parts. So this is -1 plus 3, all right, which is +2. So plus 2i. That's it. All right. It's essentially the same also as just combining like terms, right? Your constant terms here, 3 and 2, are like terms. And your imaginary parts, -i and +3i, are like terms. So -i plus 3i, of course, is plus 2i. All right, so go ahead and take a moment to kind of work these next few out on your own. Okay, so let's take a look at these. All right, so here, of course, we have 1 minus 4, so that's going to be -3. And then we have 2i minus 2i, which is just 0i. So you don't even have to write it. Just -3 is perfectly sufficient. Now, of course, if you put plus or minus 0i, whatever, that's fine. All right, so here, all right, now we kind of do need to be careful, all right, especially when we're subtracting negatives. So 3 minus -2, all right, is going to be 5. And then 0i, all right, minus 3i will be -3i. And then we still have our plus -5 plus I. All right, so 5 plus -5 is 0. All right, -3i plus I, all right, is -2i. Again, if you put 0 minus 2i, that's fine, but it's not needed. All right, and then here we have 3, and you can kind of do them all at once too if you want. Here we have 3 plus 4, which is 7, and then minus 7, which is 0. So those are all gone. All right, and then 2i plus -i is just I, and I minus I is 0, right? So there's nothing here, just 0. Okay, so many properties of real numbers are valid for complex numbers as well. All of the properties hold. All right, commutative properties of addition and multiplication. So that means it doesn't matter the order in which you add or multiply complex numbers. Associative properties of addition and multiplication. Distributive properties of multiplication over addition. All right, you don't really have to think about these. They're just kind of intuitive, right? Just do math like you've always done math, and these things will work. All right. Multiplying two complex numbers is similar to multiplying two polynomials in combining like terms, as in the FOIL method. All right. So, for instance, we'll look at a couple of these. All right. So here we can simply distribute. All right. So we're going to get negative 10 plus 15i. All right, here you can distribute again, which, with binomials, I'm sure a lot of you think of this as foiling, right? I think of it as distributing. So first I distribute the 2. So we're going to get 8 plus 6i. Then we distribute the negative I. So negative 4i minus 3i squared. All right, now do be mindful, we just talked about I squared, and I squared is equal to negative 1, right? So negative 3 times negative 1, this really becomes positive 3. All right, so we have 8 plus 3, that would give us 11, and 6i minus 4i would give us positive 2i. All right, go ahead and use those examples to kind of, figure out these next few problems, and I'll go over the answers here shortly. All right, so let's go ahead and take a look at these. Again, here we can just go ahead and distribute. So first I will get 9 minus 6i. Then I distribute here, and we will get plus 6i minus 4i squared. Again, minus 4i squared is negative 1. Negative 4 times negative 1, this is really positive 4. Of course, my minus 6i and plus 6i cancel out here. So 9 plus 4, this is just 13. All right, now, it's very important to notice something here. All right, see how these have the same pieces? It's just that this middle sign here is opposite. Those are what's called conjugates, okay? In this case, they're called complex conjugates. Right? And it's very important to note that when you multiply complex conjugates, you always just get a real number. Okay? We're going to be using that concept here in a little bit. All right? And then, of course, here we can distribute as well, and we will get negative 4i plus 20I squared. So plus 20I squared is really just negative 20. So if we want to write this in standard form means we always write the real number first. All right. So this would be negative 20 minus 4I. All right, here, of course, when you square something, you're really just multiplying that thing by itself. All right, again, please don't think that you just square both pieces on the inside. All right, that never works. So here I'm going to first distribute my 3, and I will get 9 plus 6I. Then I will distribute the 2I, and we will get plus 6I plus 4I squared. Of course, plus 4I squared will just end up being negative 4. All right, so here we have 9 minus 4, which is 5, and 6I plus 6I, which is 12I. And that's it. That is in standard form. Any questions or concerns there? Okay. So complex conjugates, what I just kind of talked about. All right. The product of two complex conjugates yields a real number. Complex conjugates are of the form a plus bi and a minus bi, and their product is a squared plus b squared. All right, so that is a very important especially this part here, right? You can. I mean, I never really think of it like this. I just go ahead and like multiply it out, and then I know the middle terms are going to cancel. Okay, so multiply each of the complex numbers by its complex conjugate. All right, so if we have 1 plus I, then its complex conjugate must be 1 minus I. All right, so when we multiply this, we will get 1, and then we will get minus I plus I, which will cancel out, and then minus I squared. Of course, minus I squared is plus 1. So this is just 2. Go ahead and take a moment to multiply 3 minus I by its complex conjugate, 3 plus 5I. All right, so this, of course, goes relatively quickly. All right, 3 times 3 is 9. All right, then we get plus 15I minus 15I, which cancel, and then minus 25I squared, which, of course, this just becomes plus 25. So this ends up being 34. Good times? Great times had by somebody somewhere. Okay. Oh, wait. Did I just mess up somehow? Okay. Sure. Okay. So here, right? 3. Gotcha. Okay. So 3 times 3 is 9. All right. Then you get plus 15I minus 15I. Those just cancel. Okay. And then you get minus 25i squared. Well, I squared, again, is just negative 1. So negative 25 times negative 1, this whole thing just becomes plus 25. So 9 plus 25 gives you 34. Fair enough? Everybody good? Okay. To write the quotient of a plus bi and c plus di in standard form, you need to multiply the numerator and denominator by the complex conjugate of the denominator. All right, this is very important. This is how we divide, all right, complex numbers. And it's all Jasmine's fault. Your fault. You shot the clerk. Right? That's from a movie.
So what we just did was conjugate multiplication.
Yes. All right, and we're going to use that idea here to actually do division. So let's take a look. All right, so let's write the quotient. Who's that? What? I mean, I probably would have. If you don't know how to do it already, then yes, I would definitely have written that down. Usually when I just sit there on a screen and like I'm just kind of hanging out, it's because I'm giving you time to write it down.
I usually just
Okay. Still slacker. Sweet. Jeebus. We're good? All right. No problem. Okay. So if we're trying to do 2 plus 3i divided by 4 minus 2i, all right, that last slide said to multiply the numerator and denominator by the complex conjugate of the denominator. All right. Not really. Here we're just multiplying both by 4 plus 2i. All right. And the reason why we're going to do that is because we don't want, like, I essentially is the square root of negative 1. And remember, it's not proper in mathematics to have a square root in the denominator. All right. So this is essentially getting the I, which in turn gets rid of the square root, from the denominator. All right. So now when I go ahead and distribute all this stuff out, in the numerator, I'm going to get 8 plus 4i plus 12i plus 6i squared. And the denominator, I'm going to get 16 plus 8i minus 8i minus 4i squared. So, of course, the minus 8i plus 8i will just cancel. Of course, again, minus 4i squared just becomes plus 4, right? Because this is negative 4 times negative 1, right? So now combining like terms, right? Oh, well, and of course, this plus 6i squared becomes negative 6, right? So 8 minus 6 is 2. 4i plus 12i is plus 16i. And then in my denominator, 16 plus 4 is 20. Okay, now, they will want us to simplify this because we want it in standard form, right? So we want it to look like a plus bi, not a plus bi over something, right? So this is really going to be 2 over 20 plus 16i over 20. So we just reduce these things and we get 1 over 10 plus, right, and this would be 4/5 times I. So my A would be 1/10 and my B would be 4/5. So that is how you do division with complex numbers.
So we just do it like that?
Absolutely.
After we get it, we just separate it?
Any questions or concerns there? Yes? Somebody? No? Let's try another one. You guys go ahead and try this one. Remember, we are just multiplying the numerator and denominator by the complex conjugate of the denominator. Okay, so this one goes relatively quickly. All right, we have 2 plus I over 2 minus I. All right, and the complex conjugate of the denominator is 2 plus I, so we multiply numerator and denominator by that. Here we will get 4 plus 2I plus 2I plus I squared. Over here we will get 4 plus 2I minus 2I minus I squared. So of course these cancel, and minus I squared just becomes positive 1, and plus I squared just becomes negative 1. All right, so here we're going to get 4 minus 1 is 3, plus 2I is 4I, and that's going to be over, all right, 4 plus 1 is 5. All right, so this will be 3/5 plus 4/5 I. And that's it. Questions or concerns there? Sweet. Okay. So the principal square root of a negative number, right? If a is a positive number, then the principal square root of the negative number negative a is defined as right? So the square root of negative a is equal to the square root of positive a times I, right? Whenever you have a negative under the square root, basically you just pull the negative out, it becomes an I, and then you do everything else like normal. Okay.
Wait, is the I outside of the?
Yes, absolutely. The I is 100% outside of the square root. You can, yes. In fact, oftentimes you see it like this. Um, Whenever a is not a perfect square, just to emphasize that the I is not under the square root.
So you can write it like that instead.
You can. Okay. So let's take a look at some. All right. And some are easier than others, right? Now, there's multiple different ways that you can do this. I'll show you some. All right. First, I'll show you using kind of what they want you to use since we just learned it, but that's not totally necessary, right? So here, this would really be I times the square root of 3, right? And then this would be I times the square root of 12, right? Well, if you went ahead and multiplied here, you would get I squared times the square root of 36.
And then that's just
Right. See, so this is negative 1 times 6, which is negative 6. All right.
wait, but the square root of 36 it can be negative or minus.
Yes. Right. So you actually can say that this is plus or minus, which is why I don't like to do it this way. There's a much easier way. What's negative 3 times negative 12? What's the square root of 36? Plus or minus 6. You're done. Well, you don't even have to mess with the i's at that point. Right? I mean, that's how I would do it. Right? I wouldn't even deal with the i's in that case. All right, now sometimes you're going to have to, right, when these things aren't perfect squares. All right, but you can break them down into things that are perfect squares. All right, so remember, of course, our perfect squares 1, which really never helps us, right? 4, 9, 16, 25, 36, right? So on and so forth. All right. So do any of these go evenly into 48? Yes.
Yes. 12 times 4.
What's that?
12 times
12 times 4, I would even argue that there's a bigger one. 16 and 3. Yeah. right? So I would actually change this to the square root of negative 16 times the square root of 3. All right, what about negative 27? Does a perfect square go into there? Yes, all right. And I would say that that is the square root of negative 9 times the square root of 3. All right. Now, what's the square root of 16? 4. So what's the square root of negative 16? 4i. All right. So this is 4i times the square root of 3. All right. What's the square root of negative 9 here? 3i. All right. And then, of course, we have the square root of 3. All right. Now, once when you have the same radical, the same square root over here, we can treat this like terms, right? Think of this as like our x, right? So if I had 4ix minus 3ix, what would I have?
I square root.
Yes. So this is going to equal I times the square root of 3. And that's it. No. All right. And here,
Square that, what you just get 9. Or, no, just negative 3.
well, remember, we're going to have to be careful, right? Because when you multiply,
Oh, yeah.
when you square things, you have to multiply it by everything, right? So here, when we distribute, we'll get 1 and then minus the square root of negative 3. And then here we will get minus the square root of negative 3. All right. And then here we would get plus the square root of 9. All right. Now we do have to be careful here because this is going to be like plus or minus 3, right? And this is going to be essentially we have 1 minus I times the square root of 3 minus I times the square root of 3. All right. And then we're going to have essentially plus or minus 3 here. All right. So here we're going to get minus 2i square roots of 3, right? If I have negative 1 of something and then I take away one more of that thing, I have negative 2 of that thing. All right. So here, when you have 1 plus 3, you're going to get 4. All right. But when you have 1 minus 3, you're going to get negative 2. All right, so you would actually have 2 solutions there. One with the positive 3, one with the negative 3. Good times? Had by somebody? Somewhere? Okay. All right, so let's solve the following quadratic equations. All right, so this one, of course, there's a couple of different ways you can do it, but the easiest way, all right, is to just subtract 4 from both sides, and then take the square root of both sides. X is going to equal 2i. All right, here, right, now we can try to factor this, right? This is going to be 15 and negative 2. All right, so nope. Well, you would like to think that, right? But that product is actually negative 15, right? So, of course, that's what I thought first initially too, but you kind of have to check yourself, and that's actually not going to work. So here we're going to use the quadratic formula, right? Which often this is what you have to use when you know you're going to get some imaginary number, all right? So Here we get x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. All right, so we're going to get 2 plus or minus the square root. This is 4 minus 60. So this is negative 56, right? All over 6. All right, so what perfect square goes into 56 nicely? Well, 8 isn't a perfect square.
Oh,
Yep, I hear you. So 4 does, though. All right, I think 4 goes into this 14 times. So this is essentially 2 plus or minus 2 times the square root of negative 14 over 6. So this would be, and since all of these things are divisible by 2, we can actually do this. So this will be 1 plus or minus, and this would just be I root 14 over 3. And you could just leave it like this. That's perfectly acceptable. Of course, if you really wanted to put it in standard form, although it doesn't tell you to here, so you wouldn't have to, you would say 1/3 plus or minus the square root of 14 over 3i. But they didn't tell us to here, so we don't have to. I don't think this part of it is, but everything else is. Okay, obviously that's not your homework. All right, so your homework is on Delta Math. So you can have the rest of the class to work on Delta Math.